We can use what we know about how conic sections reflect light to try to build a better telescope. As usual, pause this video and try these problems before you continue on watching me solve these problems. Okay, so the idea here, I think we've talked about in the past how a parabola can be a good part of a telescope. A parabolic mirror can be a good part of a telescope because if you have light coming in from faraway stars, that light is essentially parallel. So if you have your telescope lined up right, a parabolic mirror will reflect those incoming light rays towards some focal point. And one of the jobs of a telescope is to gather up light from a dim object and concentrate it all into a point so that it appears brighter. And a parabolic mirror will evidently do that. So to build a telescope like this, one of the things that you have to do is decide what the focal length of your parabolic mirror is going to be. So we're going to start with a parabolic mirror that has a focal length of 1,000 millimeters. So remember, that's the distance from the vertex of the parabola to the focus of the parabola. This 1,000 millimeter distance is kind of a typical distance for a very small hobby telescope. Okay, so let's find the equation of this parabola that has a focal length of 1,000 millimeters, that is 1 meter, and that opens to the right, like I have in the picture here. So because it opens to the right, we should use the version of the equation of a parabola where x is unsquared and y is squared. Okay. When we write down this equation, we are putting the vertex of the parabola at the origin, right? So this parabola is unshifted, so its vertex is at the origin. Our focal length A is 1,000, so just put that in here, and you get 4,000 x equals y squared. Okay. So what will the path of the incoming light rays be as they reflect off the parabolic mirror? Well, light rays coming in parallel to the axis of the parabola reflect towards the focus. That's why the focus is called the focus. It's because it's where the light gets focused. Oops, excuse my bad drawing. This is hard to do on a drawing tablet like this. All of these light beams get reflected towards the focus. Okay, which is pretty good. That's what we wanted from our telescope. We wanted this mirror to focus all of the light to a single point. Unfortunately, doing it this way has a couple drawbacks, so which I discussed down here. So the drawbacks are, first of all, this makes for a very long telescope because it has to be 1 meter long. If you want sort of a more powerful telescope, it turns out you need it to be longer. And so this 1 meter telescope, right, 1 meter might not sound too long, but it's only going to get longer if you want a fancier telescope. The second drawback is that, like, if all the light is being focused at this point here, like, that's where we need to put our eyeball so that we can look at all of that light. In fact, we'll put a telescope eyepiece here, but anyway, we need to stick our head right here so that we can look at that light, but that's going to block incoming light, right? We don't, our whole body is going to be down here. We don't, this is a very inconvenient place to have our focused light because it's in the way of the incoming light. So we need to figure out a way to fix that. What we really need to do is adjust our telescope system so that all the light gets focused down to a point that is somewhere more convenient than where we have put it right here. There are kind of two ways to adjust this system to make that happen. There's kind of a simple way and a more complicated way. The simple way, which we are actually not going to do, but how you make it happen is if you put a flat mirror at an angle in here, it will reflect the light out sideways. And then you can put your head there to look at the light coming out the side of the telescope. Telescopes that work that way are called Newtonian telescopes. You can maybe guess who invented them. But the other way to make a telescope that has the focal point in a more convenient place is, instead of reflecting the light out the side of the telescope, we could reflect it out the back. So we could somehow come up with another mirror to stick into this telescope so that the light bounces first off the parabolic mirror, then off this other mirror, and then is focused towards this focal point that is behind the parabolic mirror. We will have to drill a hole through the parabolic mirror to let this light through, but it's a pretty small hole. You can see it doesn't have to be that wide. Doing it this way has two advantages. So the first is your telescope can be quite big, and you're always going to just be sitting at the back of the telescope, which is pretty convenient. The second advantage of doing it this way is if you look at how the path of the light is folded up like this, that means because it's folded up like this, the telescope will be a lot shorter than it would have to be otherwise. So this is a very convenient way to make a telescope. It makes a relatively portable telescope. I mean, powerful telescopes are going to be big no matter what you do, but this gives you a smaller telescope than you'd otherwise have. But now we have a couple questions to answer. The main one is, what shape will this mirror have to be so that it reflects the light to this back focal point that I've called F2? And then the second thing, so you might guess it's some kind of conic section, and that's true. But once you've decided what kind of conic section, we will also need to decide where should the foci of that conic section be to achieve the reflection that we want. So take a second to think over these two questions and try to come up with an answer. Okay, so figuring out the conic section is really, the key words here are light going towards F1, and we need to reflect it so that it's going towards F2. So if you remember the conic sections we have available to us, there's a parabola, an ellipse, and a hyperbola. Right? Parabolas reflect parallel light towards the focus, and that's not what we're trying to do, right? Because for this second mirror, the incoming light is not parallel, so we don't want a parabola. For an ellipse, rays that come from one focus reflect to the other focus. So from one towards the other. But that's not the kind of reflection we want, because our light is going towards one focus and we want to send it towards the other. So it's not an ellipse either. So maybe it's a hyperbola. The reflection property that we figured out for hyperbolas is that rays coming from one focus reflect so that they appear to come from the other focus. Well, that seems like that's not what we want either, because, right, if you listen to what I just said, it was about light coming away from a focus, light coming from a focus instead of going towards a focus. But, I mean, if light can go if light is reflected out of the focus of the hyperbola this way, we could think about light coming towards the focus, just sort of run the light beams backwards, kind of. So if you run this reflection property backwards, it says that light headed towards one focus is reflected by a hyperbola towards the other focus. And that's exactly what we want. We want light coming towards one point to go towards another point instead, and a hyperbola will do that. So we need a hyperbola here. So we're going to have to make this second mirror a hyperbolic shape. Okay, so where should this hyperbola have its foci? Well, clearly F1 and F2, right? Because if we have the foci of this hyperbola at F1 and F2, then light going towards F1 will be reflected towards F2. So this F1 is kind of doing double duty because it's a focus for the parabola and also the hyperbola. And that double duty for this focus is what makes this style of telescope work. All right, so now that we know the right shape, the right kind of shape for our hyperbola, we can actually figure out what the equation of this hyperbola is. You might need to figure out what the equation of the hyperbola is so that you could draw it accurately, or so that you could make the mirror, or so that you could simulate the mirror in some simulating software, I guess. To determine exactly what shape this hyperbolic mirror is, though, we need to choose some lengths. So I've made some choices here. So the distance of this rear focus from the parabolic mirror, we're going to say that that's 100 millimeters, so 10 centimeters, that's about 4 inches. So your face is going to have to be 4 inches from the back of the telescope. That seems like a decent distance, not too big but not too small. Also, we need to decide how far away from the parabolic mirror our hyperbolic mirror will be, and let's say that's 500 millimeters. And also remember that the focal length of our parabolic mirror is 1,000 millimeters. So with all those lengths in mind, see if you can figure out the equation for this hyperbolic mirror. Remember, we already have the parabolic mirror, the equation for the parabolic mirror. We found that earlier. And when we did that, we put the origin right here at the vertex of the parabolic mirror. So with all of this in mind, find the equation of the hyperbolic mirror. Okay, so to find the equation of the hyperbolic mirror, I mean, you can tell that these foci for the hyperbola, F1 and F2, are not equally spaced around the origin. So the center of this hyperbola is not at the origin. We need to find the center. Well, we know where both of these foci are going to be. This focus over here is at, let's see, we put the origin at the parabolic mirror vertex. F2 is to the left of that, so it's negative 100, 0. That's F2. And F1, well, remember, F1 is the focus of the parabola, so the distance from the vertex of the parabola to the focus of the parabola, that's the focal length, that's 1,000. So that means F1 is the point 1,000, 0. Okay, well now that we know where both of these hyperbola focuses are, we can find the center of them, or the midpoint between them, because that will be the center of the hyperbola. So let's see, halfway between minus 100 and 1,000 is at 450, I guess? 550. 550. So the center is at 550, 0. Okay. So this is the center of our hyperbola. And now we can also figure out the distance from the center out to one of the focuses. So this is actually no, this should be 450, shouldn't it? 450, right? Because now it's 550 millimeters to the right to get to the one focus, and 550 millimeters to the left to get to the other focus of the hyperbola. Okay, and that, so 550 millimeters, so that's the distance from the center to a focus, so that's C. That's the focal length for the, or the focal radius for the hyperbola. So we know C. If we can find A or B, then we'll be able to figure out the equation for a hyperbola, for the hyperbola. And well, look, we should be able to figure out the distance. We should be able to figure out the distance from the center of the hyperbola over to the hyperbolic mirror. In other words, the vertex, right? So the distance from the center to the vertex. So the center is at 450, and the vertex is over at 500 millimeters, and so the distance between them is 50. So I've made a mess here, but the distance from the center to the vertex of the hyperbola is 50 millimeters. All right, well this is enough to figure out the equation of the hyperbola. So we have the center is 450, 0, A is 50, and C is 550. Okay, so to write down the equation of the hyperbola, we need to also find B, right? And for a hyperbola, C squared is B squared plus A squared. So, let's see, calculator time. So 550 squared. So let's see, 550 squared equals B squared plus A is 50, so 50 squared. So B squared is 550 squared minus 50 squared. So that is 300,000 millimeters. So that's B squared. And so B is just the square root of that. Okay, so for the equation of the hyperbola, It's opening left and right, so our x term will be positive and our y term will be negative, like this. There's no shift in the y direction, right? So we'll have a -0 there. For the shift in the x direction, we need to shift right 450, so we'll put -450 right there. And then, let's see, under x we need a squared right there, and a is 50, so that's going to be, what, 2,500? And then under y we need b squared right here, and b squared is 300,000. Equals 1. Okay, so here's the equation of our hyperbolic mirror. So now we could simulate it, we could manufacture it, and then we could actually build this telescope. This style of telescope is a telescope that gets used mainly if portability of the telescope is an issue. If you have like a large fixed space for your telescope and you're not going to move it, then make the telescope as big as you want. It doesn't really matter. But if you need a telescope that you're going to move around, then this folding up that I talked about earlier, the way that the light path is folded up, makes the telescope about half as long as it would have been otherwise, which is a pretty good advantage.